Just to push the idea that the diagonal can be of any size at any angle, this is a much larger diagonal placed between these boundaries. But everything else is the same. Using this vertical, these divisions can be transferred over to the bottom plane. And comparing that to the geometrically divided fifths, we can see that these lines match up. Moving on to 3-point, now we have a vertical face on the right side of the perspective square, and it's been divided into thirds using those diagonals, that geometric proof. The diagonals are going vertically down to the third vanishing point and horizontally to the right vanishing point. Zoom in here, we can see that these thirds on the vertical plane are intersecting with thirds on this y plane. So now we can test the same methods, but now in 3-point perspective. This is an area where, at least when it comes to instruction, these kind of methods seem to break down. I've never seen them discussed anywhere, and it's possible that I'm not aware, but I haven't seen this in books or in videos. Maybe someone's talking about it and I'm just not aware of that, but for this video I had to figure out these methods on my own. Luckily they're simple enough and the rules are simple enough, and I will discuss those rules as we go along. Essentially, the idea is the same. You just have to be aware of what vanishing points and what horizon lines you will be aiming for, since now there are essentially 3 horizon lines, but we'll be using 2 of them. For the first example, this is dividing this vertical face into thirds using the same cornrows method used on the y-plane. And this is using the same left vanishing point, essentially creating a plane in 2-point perspective, the upper y-plane or top of the box in this case. Where these lines intersect, the vertical plane, this x-plane, the lines can be made perpendicular, cutting the face of this side into thirds vertically, and with the diagonal from corner to corner, those same divisions can be taken horizontally. Since this is a plane in 2-point perspective, all the other divisions that were performed on this lower y-plane that were in 2-point perspective could be used in the same manner. Even though those divisions were on this edge, they could be taken up and you would have the same result. Speaking of 2-point perspective, this is a method commonly used in 2-point perspective. Once this line is drawn parallel to the horizon line, you can take lines that are perpendicular to it and place a diagonal at any random degree. The benefit is you can use a ruler and say you need 3 even spaces. It could be inches or centimeters or any other measurement, and you can rotate the ruler between these 2 bounding lines until the 1 and the 3 line up or intersect these bounding edges. Marking those points and then moving them directly parallel to these boundaries down to this original picture plane line will result in the same intersections and therefore the same divisions on this face. This really wouldn't be practical in software. It is definitely practical in traditional art, barring a tool such as an equal space divider. This is back in 3-point perspective, still dividing the side of the square into thirds, using the same methods that were used in 2-point perspective, but this time having to use either a third vanishing point or another horizon line. In this case, it's the same cornrow method, but the resulting plan or grid is much larger because of the type of convergence that the third vanishing point establishes. So this diagonal is placed between the converging lines heading to the bottom vanishing point, and it is also parallel to this horizon line. Now, if this was constructed on the other side, it would have to be the same, and there would have to be, this horizon line would have to be plotted out so that this diagonal, or the resultant diagonal, could be parallel to it. Once those requirements are fulfilled, this diagonal can be divided into thirds and taken down directly to the bottom vanishing point. And as can be seen here, the resulting lines intersect right on the thirds of the side of the face, or the side of this cube, in the same place that the diagonals would create thirds. Here's a closer look at the intersections. This is taking the concept of creating this outer boundary and placing a random diagonal that's been divided evenly. But again, the construction is much larger since we need to meet those requirements stated earlier. But the method, the concept, everything is the same. Taking these measurements directly over to this line parallel to the horizon, we end up with the same result. These constructions become inefficient and aren't really practical for digital or traditional. For obvious reasons, the canvas size would have to be substantially larger than the drawing area. This is an example of using a special vanishing point in three-point perspective. The special vanishing point is intersecting this horizon line. Otherwise, everything else is essentially the same. Everything's been tested, all of the points snapped to the coordinates are the same, and the lines from the special vanishing point intersect their correct corresponding positions. And basically what this is, or another way of looking at this, is if this grid was rotated so that this horizon line was horizontal, then this is just a two-point perspective setup. This would be the left vanishing point, this would be the right vanishing point, and this would be the third vanishing point. All of these vanishing points, including the special vanishing points, and these constructions or these plans, could be plotted by estimating the convergence. You could even estimate the convergence to a special vanishing point on another horizon line, and sometimes these horizon lines are really close to the drawing area, so you could take a few corners, take this diagonal for example, and if you were to multiply this square and take another diagonal, you could plot at least this point for this horizon line. So a lot of these things could be estimated, but there are too many obvious issues with these constructions. First of all, they're too large. Another one is, since these constructions are larger, these lines become longer, increasing the chance for error. Also, there's more and more to remember or memorize when it comes to these constructions, especially as the perspective construction becomes more complex.